Okay, so we're going to break things up first into our free body diagram. So when we do a free body diagram, we want to take the object with mass, which is going to be our board, and we're going to kind of like separate it. Okay, so we have what we talked about. We have a pivot on the end. So if we scroll up and we look at our pivot and what our forces look like for our pivot, this would be our pivot here. Okay, so we have our X and Y forces. So we're going to call them they call them V and H. I think that's a little unusual. I usually call them like FX and FY. Whatever you label them, it's fine. It's up to you. So over here, where we have this guy right here, we're going to put a normal force also coming through the board here. Then midway through the board, so this is very important. Whenever we have an object and it's like a weird shape, we're going to model the weight at the center of mass. So this is 49 newtons. So that's in our problem. We know that I think we're given the weight of the board. Okay, 60 kilograms. We're given the weight of the board here. Oh, sorry, the board is 5 kilograms. Yeah, so 5 kilograms, right, times 9.8 meters per second squared is going to give us the weight of the board. So we're modeling that just at the center of mass, okay? Then we have the person on the end here. So our person on the end also has weight, right? And so we're going to put the weight at that point. We have 588 newtons, which is just the 60 kilograms times gravity. So that's 60K times gravity. Okay, so those are all of our forces that we have here. So we have this axis that we're going to choose as our rotation point, and then we just basically put all the forces on the board. So we put them all on there. Okay, so next what we're going to do is we're going to look at sum of forces in the X, sum of forces in the Y, and then the torques. So X, Y, and torques. And because the system is in static equilibrium and we know we're dealing with statics, we can say they're all equal to 0, but we need to find out what that 0 value is, right? We need to figure out all of the things that are going to be counteracting each other that are going to give us that 0 value. Okay, so the best choice, when you're dealing with these problems, you can choose your axis of rotation to be anywhere. Like you can take the sum of torques at any point and then set them equal to 0, because all of the forces should be balanced, right, at all points of the board. If it's not rotating, that means at all points when we take the torque that things should be balanced. But to make it easier for yourself, it's always best to try to choose the rotation point as the one that has the most forces. Okay, so we have 2 unknown forces at this point. We have no idea what they are. And so if we take this to be our rotation point, these forces are not going to contribute any torque, right? Because if we think about our sum of torque equation, torque is equal to RF sine of theta. We need some radial distance away, right, from a rotation point to cause torque. So if we take it at this point, we can ignore those 2 forces. So it's just kind of like a trick, basically. Okay, so let's think about first, we're going to do everything in the X direction because I think that's our easiest one. So in the X direction, we only have that H force, okay? We only have that H force. In the Y direction, we have V and N as positive, and then we have 49 and then 588 newtons as negative. So we're just going to put those there. So V plus N minus 49 minus 488, right? And then for our sum of torques, that's where our rotation point comes into focus here. So we're going to take this to be our point of rotation. So we're just looking at our sum of torques equation, right? And we are going to, our R is just going to be the distance, right, between these guys here. This is the R for each torque that we do. Obviously, it's going to be a different length. So we're going to just take the distance for R, the force, right, for that F, and then sine theta is going to be these angles, right, between the R distance away, and the force itself, okay? And so in this case, it's 90 degrees. So for all of them, they're just going to end up turning into this like RF, because sine of 90 degrees is 1. Okay. The last thing we need to take into account is whether our torque is positive or negative. So if we go up, we're going to be causing counterclockwise rotation, right? If we think about that, where if we push up, we're going to cause it to rotate counterclockwise. And then if we push down, right, we're going to be causing it to rotate clockwise. The sign convention for torque is positive is counterclockwise and negative is clockwise. Okay, so let's think about the sign conventions for each of these. And let me go ahead and write the distances on the board. So between this and the normal force, normal force coming up just from that board, this is 1 meter. The 49 Newton force, we had to take it at the center of mass for the board, which is just the geometric center, and that is 1.5 meters. Okay, and then this guy is acting at the end of the board, and the end of the board is going to be 3 meters, right? Okay, 3 meters to the end of the board. Okay, so let's do our sum of torques equation. Okay, so these two are a distance of 0 away from the pivot point, and so we are just putting 0 torque for each of them for both of those forces. And then the H force is also horizontal, so it wouldn't be the angle is 0 degrees, so it's radius is 0 and angle is 0 for that one. Okay, what about these two? So N, we have 1 meter times N, and we're going counterclockwise, right? Because this would cause it to rotate up. So that would be a positive torque. Okay, this guy though is going, would cause it to rotate clockwise, right? Around this pivot point. And so this would be a negative torque. So those two would both be negative. So minus 1.5 meters, because we found that to be our distance, right? So it's just our R, right? And then times 49 newtons minus 3 meters, because that's our distance there, and then times 588 newtons. Okay. Are we forgetting anything here? So the only unknown in this equation is this n, and we set that equal to 0. So because n is our only unknown for that one, I think it should be pretty straightforward. So basically, this would be like you plug it into a calculator. So your n would be equal to 1837.5 newtons. Okay, so that would be our normal force. Okay. We also don't know our V force here, but now that we found our normal force, all we need to do here is basically just plug it back into that equation up there, right? So we can take our normal force, and then we can take this guy, right? And then we could plug our normal force in after we found it, right? And then we could just solve for V. So in this case, and we know that this is equal to 0, right? Because we're dealing with statics, everything's going to be balanced. And when we plug that in, we can also get a value for V. So V is going to be equal to, just after some, so 1200.5 newtons. Okay, so that's our final solution for V. Okay, so to summarize what we did was we basically, so we looked at our, how our forces would be modeled at our pinning points. So this was a point where it was just resting on a frictionless surface. So we just had a normal force. And this was a pivot. And so for the pivot, we went up here, we looked, we found this is how we model our pivot. And then for the resting on a simple frictionless surface, we looked at this one and we found that that's how we would model that. Okay, so I will go ahead and stop this one, and then let's go on to the next problem. It's going to be a little bit more complicated.